Caverns. Being a native Virginian, they are near and dear to my heart. I have many fond memories from my childhood of marveling at the massive pillars, stalactites, and other distinctive features in the caverns under the Shenandoah Mountains. Have you ever wondered how these features came to be? They weren't always there. These massive underground voids and their complex and beautiful adornments took millions of years for Mother Nature to create. Geologists now understand how these structures formed and how they're changing today because of our understanding of the process of dissolving and depositing various minerals. These wonders of nature were not created with excavators, chisels, or any other tools created by man. They were created with nothing more than time and the most abundant liquid material on Earth, water. Water is sometimes called the universal solvent. It's a somewhat fitting name for this material that seems to be able to solvate so many materials with which you're familiar. Just think of all the aqueous or water-based solutions that you encounter on a daily basis. Coffee, tea, and other beverages are water-based solutions, for example. Water can even literally move mountains as rain slowly dissolves solid rock over the eons. But of course, water isn't really a universal solvent. There are clearly some things that it does not dissolve. Oil, when it spills onto the ocean, doesn't dissolve. It simply floats on the surface of the ocean, causing environmental calamities as it accumulates on shore. So, water really might be a very versatile solvent, but to call it universal is a bit of an overstatement. So, what determines what dissolves in water and what does not? Chemists use an old idiom that helps us understand this. We say, like dissolves like. What we mean by this is that water, being a very polar substance, can form better interactions with polar hydrogen bonding or ionic solutes, like sugar or salt. Remember from our previous lecture on ionic solids, that massive lattice energy that sodium chloride has? Well, that was a measure of the energy needed to separate the ions in a vacuum. This amount of energy is tremendous, but put sodium chloride in water, and just a little stirring is all it takes to completely disassemble the crystalline material. So what's going on? What makes the difference? The difference is that when an ionic solid dissolves, its constituent ions are dispersed not into the gas phase, but into liquid solvent. Water, being so polar, can arrange itself around the ions in such a way that it stabilizes those ions. Now, before we go any further, it's important for us to acknowledge that solubility is finite. And what do I mean by that? Well, let me show you. I've got 3 containers here. I'm going to fill these 3 containers with water. It's given volume. It doesn't matter what volume it is for now. And then I'm going to add to that a solute. I've done a cartoon version of sodium chloride here. So let's throw a crystal of this cartoon sodium chloride into the leftmost container here. Now, experience tells us that when we add a small amount of a salt like sodium chloride to a large quantity of water like this one, it's going to dissolve, break down into its constituent ions, and basically occupy the entire volume of that solvent. Now, let's make an even stronger solution of that salt. I'm going to add not just 1, but 2 equivalents of this sodium chloride, and lucky me, the second one is dissolved. And notice that it's created a solution of greater concentration. There are more dissolved ions in the liquid. But at some point, something happens. At some point, I can add an equivalent and have it dissolve just as before. I could even add a second equivalent. It'll dissolve just as before. But when I add a third equivalent in this situation, nothing happens. The crystal simply rests at the bottom and doesn't dissolve. So why is it that the first 2 crystals that I added dissolved so easily, and yet at some point I hit a wall, if you will, of solubility, a limit at which I can't get any more solute into my solution? The reason that I hit that limit, known as saturation, is that in order for something to dissolve in a solvent, those solvent molecules have to interact favorably with that solute. So here's a slightly more detailed graphic showing what we just accomplished before, adding successive equivalents of sodium chloride here to our solution containing water molecules. Now I'll call your attention to the one on the left here where we've added just a small pinch of sodium chloride. And as that dissolves, it becomes ions, positively charged cations, negatively charged anions, which move into solution. But notice that the solution is interacting with those ions very specifically. Right? They've created these sort of spheres of hydration, if you will, around them. You'll notice that the water molecules here are pointing their dipoles in towards the chlorine, in this case, with the positive end facing the chloride anion, versus our sodium cation here, where the negative end of the dipole is facing inward. And it is that stabilizing interaction that makes sodium chloride soluble in water at all. Now, we added some more sodium chloride in the second vessel, and we saw that that dissolved as well. And obviously, we could expect that because we have plenty of water around here to form those spheres of hydration around my ions. But at some point, depending upon how strong these interactions are and how many water molecules tend to associate with a given type of ion, we find that we reach a limit where there simply isn't enough water left to completely complex it. And that is the point of saturation. So here in my third example, I still have the same amount dissolving as previously, and I have two ions left behind with not enough solvent left to form an effective complex, thereby solubilizing it. So the only alternative for my freshly added sodium chloride is to sit at the bottom and not dissolve. This is the definition, if you will, of saturation. When we add any solute to a solution, there comes a point at which it's impossible to encourage more of that solute to dissolve. Just like a sponge that can no longer absorb any more water, a solvent can and will reach a point at which it simply cannot hold any more of a particular solute. In the case of sodium chloride, saturation happens when we add about 6 moles of salt to 1 liter of solution. So sodium chloride solutions in water are saturated at just about 6 molar. We refer to this concentration, the one at which the solution is saturated, as the solubility of that solute. So sodium chloride has a solubility of 6 molar, or about 350 grams per liter of water. That means that a completely saturated salt solution is about 26% salt by mass. The extremely high solubility of salts, like sodium chloride, is responsible for the high density of the waters of the Dead Sea, which is famous for being so dense that a human will float effortlessly on its waters due to the added buoyancy that the salt provides. The Dead Sea reached this very high salinity because it has been slowly evaporating over millennia. The water in the sea is constantly lost to vaporization due to water's inherent volatility. But salts like sodium chloride are non-volatile. They don't have any vapor pressure to speak of at ordinary temperatures and pressures, so over long spans of time, as the volume of the sea decreases, its concentration increases until it's reached the point of saturation. Once this happens, water continues to evaporate, but the remaining salt that it can no longer dissolve actually comes out of solution in a process known as precipitation. The bottom of the Dead Sea is actually covered in a bed of crystalline salt material left behind by evaporating water. Just like our sodium chloride example, it simply can't get into the solution because that solution is saturated. Steam cleaning. It's a great way to be sure that you get every unwanted bit of grit and grime off of a surface. Water itself isn't that great at dissolving a lot of things, actually, especially low polarity materials that make up most of the dirt and grime that we want to get rid of during cleaning. Now, one could use water to rinse a carpet, say, soiled with dirt or oil. You could do this till the cows come home, and it's very unlikely to come clean. But heat that water to its boiling point, and a quick pass with a steam cleaner usually takes care of the job in no time. Increasing the temperature of a solution can have a remarkable effect on its ability to dissolve certain materials that it usually can't. And this makes sense if we think about dissolution in terms of free energy. Compare our earlier sample of salt and water to the solution that it created, which has higher entropy. Of course, the solution does, because it's less ordered. So, our understanding of Gibbs free energy helps us to understand why heating water helps it to dissolve solids better in general. Increasing the influence of entropy increases the overall spontaneity of the dissolution process in this case. Now, in the case of gases, the opposite is generally true. A gas phase solute, like the carbon dioxide dissolved in a soda, would have a higher entropy when it's not dissolved in a liquid. Because out of solution, a process known as degassing or effervescing creates a gas from a liquid solution. So increasing the temperature of solutions in which gases are the solute can actually decrease their solubility. Now you can easily observe this the next time you boil a pot of water in your kitchen. You'll notice that long before the water boils, small bubbles of gas form along the walls of the pot. This is not simply water vapor. It's the dissolved oxygen and nitrogen gases in the water coming out of solution. While we're on the topic of solubility of gases, we have to consider one more factor: pressure. Higher pressures mean more gas molecules being squeezed into contact with the surface of a solution, a process which allows that solution to absorb more of that gas than we might ordinarily expect. The relationship between the pressure and solubility is known as Henry's law, and it's remarkably simple. Henry's law states that the solubility of any gas is proportional to its overall pressure above the resulting solution, and the proportionality constant from this equation is known as the Henry's law constant for a particular gas. Let's take a little bit of time and think about how the pressure of a gas above a liquid can affect its solubility in that liquid. Now, to do this, I'm going to use 3 vessels, equal in size. I'm going to add to them equal volumes of water as well, but this time I'm not going to fill them all the way to the top. I'm going to leave some headspace available here. Now, let's imagine that in that headspace, I can place a sample of gas, and I can make that gas as high or low pressure as I choose. In this case, we'll do carbon dioxide. In my leftmost vessel, I'm going to put a small amount of CO2. So whatever pressure this may correspond to, let's double that in the second vessel. So twice as many moles of gas in the same volume at the same temperature should give me double the pressure per our ideal gas law. Let's do it one more time. We'll double the pressure yet again in our third vessel by adding another equivalent of our CO2. Now, if we were to look at the solutions beneath these headspaces that are filled with gas at various pressures, we would find different amounts of that gas dissolved inside of that solution. In fact, what we would find is that as we double the pressure each time, right, we also double the solubility. Notice that here I've gone from 2 to 4 to ultimately 8, depending upon how much of this stuff I've done. So each time I double the pressure, I double the solubility. That is a linear mathematical relationship. And it's a very simple equation that leads to a very powerful law, Henry's law. And the equation is the solubility of a gas is equal to a constant called Henry's constant times the partial pressure of that gas. Now, since I've been using pure gases in my example here, the partial pressure of the gas would be the total pressure of that gas within the system and nothing else. But Henry's law is really quite interesting. It allows us to predict the solubility of a gas and how it will vary as we pressurize and depressurize that gas above the solution. So let's put Henry's law to use and solve a problem. Soda, bottled under an atmosphere of carbon dioxide gas in order to keep the bubbles dissolved into the soda before you open it. Now, typically, that headspace inside of your soda has a pressure of about 4.0 atmospheres of pure carbon dioxide. So when you open the bottle, you hear that rush of gas escaping. That's the 4 atmosphere of carbon dioxide escaping the bottle. Now, ordinary atmospheric gases rush back in, but the partial pressure of carbon dioxide drops to practically nothing. So the question we're going to ask here is this: how much gas can we expect to effervesce from a soda once it's been opened? Total. If all the gas were to escape at once, how much would we get? Well, let's figure that out. To answer the question, we're going to use Henry's law. And in order to use Henry's law, we have to go to a table and find the Henry's law constant for carbon dioxide. Now we can calculate the solubility of CO2 under that 4 atmosphere pressure of carbon dioxide. We're going to have to use a Henry's law constant of 3.1 times 10 to the minus 2 mole per liter atmosphere. And we're going to multiply that by the partial pressure of CO2. In this case, 4 atmospheres in a closed bottle. A quick unit analysis lets me know that I've got the equation right. I'm going to get an answer of moles per liter. And in this case, it comes out to 1.2 times 10 to the minus 1 moles per liter. That's the total amount of carbon dioxide that's soluble in water under an atmosphere of 4 atmosphere carbon dioxide. But once that bottle is open, something changes, namely the pressure. Notice that the Henry's law constant does not change. That's why it's a constant. But the pressure has dropped all the way down to practically nothing, about 4 times 10 to the minus 4 atmospheres, a factor of 10,000 difference, meaning that the new solubility of CO2 in your soda is only 1.2 times 10 to the minus 5 moles per liter. Now, that's so low that it's negligible. So let's finish our problem by assuming that all of the 1.2 times 10 to the minus 1 molar CO2 will be escaping. Well, 1.2 times 10 to the minus 1 moles coming from a 1 liter solution at standard temperature and pressure, we know, should occupy 22.4 liters. So when we do the math here, we get our liters for our units. We discover that about 2.7 liters of carbon dioxide will escape slowly and lazily from your soda as it goes flat over the period of a few hours. Now, there's a really great trick that's become popular in recent years that allows you to observe that effect without having to wait. We'll check that one out in just a minute. The bubbles in your beer or soda are testament to Henry's law. Of course, an ordinary, well-mannered soda drinker will enjoy the slow, lazy cascade of bubbles over the course of an hour or so until the new state of saturation is reached and the soda is rendered flat. If you're a bit more mischievous, you can accelerate this process by agitating the contents of the can, creating a number of small bubbles in the solution prior to opening it. These small bubbles act as nucleation sites, where dissolved carbon dioxide can come out of solution much faster. I recommend handing the soda over to an unsuspecting friend before you open it, though. The result, of course, is a mess, and whatever beverage can be salvaged afterwards is already flat in a matter of seconds. Even more dramatic than that result is the now popular Coke and Mentos demonstration, in which the surface of the candy acts just like the bubbles in a shaken soda, but with even more immediate results. And based on our Henry's law calculations, a gently opened 2-liter bottle of soda is primed to expel about 6 liters of carbon dioxide gas before it goes completely flat. And directing all of that gas through the narrow mouth of the bottle in such a short period of time creates a remarkable and fun visual effect. It also creates a very teachable moment about Henry's law. Now, I could make a mess here on the table by creating a geyser of soda, but rather than do that, I thought it would be fun for us to validate Henry's law. Remember, we did a calculation, and that calculation told us that this half-liter bottle of soda should be able to produce more than 1 liter of carbon dioxide when it comes out of solution, enough to inflate a balloon. So we're going to do that right now. So to do that, I placed 2 of my Mentos candies inside of this balloon already, and I'll be putting it over this freshly opened bottle of soda. Try to get a good seal here. Be sure that we don't lose any gas. All right, and now I'm going to allow those candies to fall into the soda, and that will begin that process of getting that dissolved carbon dioxide out, and we'll see just how much we get inside of our balloon. So here we go. All right. All right, we've still got some carbon dioxide coming out of there, but the process is beginning to slow down. And sure enough carbon dioxide to inflate a balloon. There's one more very interesting point that needs to be made on changing the solubility of materials. We've already established that all solutes have a finite solubility in a given solvent. We also just saw that the solubility of a given material can be altered using temperature or pressure. There's one very interesting state that we have not yet discussed, that of supersaturation. Supersaturation is a metastable state in which the temperature or pressure conditions on a saturated solution have changed so that the concentration of the solute is higher than the ordinary saturation level. One modern example of this is the nitrogenation of beers. Certain stout beers get their bubbles not from carbon dioxide but from nitrogen, which gives the beer a different flavor and a mouthfeel. But nitrogen behaves differently than carbon dioxide in another way. It tends to form a supersaturated solution when the beer is depressurized. That means no bubbles, no fun mouthfeel, no smile on a beer drinker's face. So inventive beer aficionados created a little gadget that they call a widget. A widget comes in a can of stout and has only one purpose: to release a few small bubbles of gas when the can is opened, giving a nucleation site onto which the dissolved nitrogen in the beer can effervesce. But until the widget was invented, nitrogenated beer was only available in bars from special taps, which created a turbulent flow as the brew exits the tap. When you think about it, both of these technologies essentially shake up your beer for you to get that gas effervescing and enhance the experience. Let me show you another example of this phenomenon in action, this time using a solid solute rather than a gas. We're back in Osmond Lab at Penn State University to observe the phenomenon of supersaturation one more time. But this time I'm going to use a chemical that you don't typically find in your kitchen. I'm going to use sodium acetate. Now, sodium acetate's a very interesting material. It has a much, much higher solubility in water near water's boiling point than it does in water near room temperature, like many materials. But sodium acetate's solubility is drastically different in this case. So what I've done is I've taken some sodium acetate and prepared a solution in boiling hot water, just as concentrated as I could make it. Next, I very slowly cooled that solution, and that's what's resting on the bench here in front of you. Now, you might be wondering, if I made a saturated solution at 100 degrees and then cooled it to room temperature, why is it still a solution? Shouldn't there be a tremendous amount of sodium acetate that simply can't be held by the solvent anymore and has become a solid in a process we call precipitation? And the answer is that it will very shortly. This is a metastable solution. It's not going to last forever. Eventually, it will reach that state in which we see solid sodium acetate because it simply isn't soluble enough. Now, what I'm going to do is encourage that process to take place. And the way I'm going to do it is using a little bit of solid sodium acetate as what we call a seed crystal. I'm going to place this little bit of solid sodium acetate on the top of my crystallizing dish. And what this will do is provide a surface onto which other sodium acetate molecules can begin to form a solid and grow. Now, when I pour this solution on top of these seed crystals, we'll immediately see a system that's behaving more like sodium acetate does from a solubility perspective at 25 degrees than it does at 100 degrees. In other words, our metastable, supersaturated solution will finally crash out and create new materials. Okay, here we go. I'll very gently, so as to avoid having it crystallize inside of the beaker, pour it onto my seed crystals. And as you can see, as soon as the solution hits the solid sodium acetate below, those seed crystals are doing their job and causing it to return to the state that it really wants to be at 25 degrees centigrade, which is an insoluble or lower solubility salt. Now we can see the system as it should be at 25 degrees centigrade, one in which the sodium acetate clearly is not soluble in water. Remarkable, isn't it? There was so much sodium acetate dissolved in that supersaturated solution that when it did finally precipitate, we had trouble finding any liquid left at all. Notice how similar that structure looks to the K features that we saw at the outset of this lecture. That's no coincidence. The stalactites, stalagmites, and even the bodies of caves themselves all form because of the phenomenon of saturation. My own home area in the Appalachian Mountains is famous for this. The rock in those areas consists of a great deal of limestone, which is primarily composed of calcium carbonate, a rock-forming mineral that is soluble in water. Groundwater permeates through these rocks, slowly dissolving the limestone, creating the cave formations that the Shenandoah Valley is so famous for. But now, flowing through these caves is saturated solutions of calcium carbonate. And as that water makes its way through the subsurface, it encounters the roofs of other caves and has nowhere left to go but down a growing stalagmite. As the droplet of the solution reaches the end of the line, it has one of two ultimate fates: either cling to the stalactite or fall to the floor of the cave. In either case, as the droplet slowly evaporates, it reaches the point of saturation and has no choice but to deposit its cargo of solute on whichever formation it happens to be on. This process can be extremely slow, but knowing the temperature of the subsurface, the rate of the water flow, and the total solubility of the limestone in water allows scientists to estimate the ages of these stunning features, and in doing so, to build a geologic history of how and why these caves have come to be. It's an amazing geologic story spanning hundreds of millions of years, and it's all told thanks to the most common solvent on Earth: water. So let's conclude by summing up what we discussed today. We considered the intermolecular forces that make so many salts and polar compounds soluble in water. And in doing so, we considered the maximum solubility of materials in water and the concept of saturated solutions. We investigated the effect of temperature on solutions, applying what we know about Gibbs free energy to explain why heating solutions of solids tends to increase their solubility, but those of gases tend to have decreased solubility. Next, we contemplated pressure and solubility, and we saw how Henry's law gives us a simple mathematical approximation of how pressure affects the solubility of gases. We got to witness firsthand just how drastically a little bit of added pressure can change the solubility of gases like carbon dioxide, and how we can have a little bit of fun with that phenomenon using nothing more than a simple piece of candy. Next, we tackled the concept of supersaturation, a metastable state in which a solution's concentration is greater than the ordinary solubility of the solute would lead us to expect. And finally, we looked back at an example of how solubility and saturation can explain some of the most breathtaking natural features in the world. But we aren't done exploring solutions yet. We have discussed how and why many things dissolve, but we have one more vital set of topics to cover. We have to consider some of the properties of those solutions and how mankind and nature have exploited solutions to sustain life.